present our study on the Deictic gesture-based spatial referencing for human-robot interaction and some challenges we observed in construction. So the contents are as follows. First, I would like to talk about the brief introduction of this study. In the collaborative panel installation job sites, construction robots are deployed in the field to work with human workers, but the construction environment is in dynamic conditions and has a lot of uncertainties, and most importantly, there are many as-built errors. So in this case, a human worker needs to interact with the robot, giving them spatial information of where to install the panels, and robot giving feedback its confidence to human worker. Here, spatial information is especially critical to delegating tasks to a robot. So there is an emerging need for natural human-robot communication for exchanging spatial information. Deictic gestures are generally intuitive for novice construction workers, and these gestures are commonly used in the field to direct other workers' attention to the reference, as shown in the photo on the left. Several previous works showed the performance of Deictic gesture-based spatial referencing for short distance applications, such as photo on the right, but because it has not been evaluated in a large-scale environment where construction tasks are often performed, we need further evaluation of the robot's interpretation abilities in these situations. So to sum up, our research goal is to develop the Deictic gesture-based human-robot interface in construction, especially panel installation tasks. And to achieve that, we had to first measure the robot's interpretation ability. So our research task was to evaluate the robot performance in interpreting target panels, which are located on the most common workspaces in construction, the wall and ceiling. And then we identified some challenges of spatial referencing in this large-scale environment. Next, methodology and experiment. The flowchart of the system that we used a single RGB depth camera to collect data, and then estimated 2D human pose with open pose, and then projected the 2D coordinates to get 3D human pose. And after that, we detected the pointing raycast. There are several pointing raycast models, but in this study, we used the straight line starting from the shoulder to the wrist joint. And finally, estimated the reference panel with ray plane intersection. We invited 4 participants and asked them to point at 5 ceiling panels and 5 wall panels sequentially for 13 times for each panel. Each pointing task, pointing trial, took about 5 to 10 seconds. We evaluated performance with the F1 score and distance error, which refers to the Euclidean distance between the estimated points and the real center point of the target panel. And for the results, this shows the points that robot estimated with subject number 1. And we could observe quite consistent results, although it's quite hard to identify certain tendencies. Now, with the 2 performance metrics, the overall performance of distance error was about 0.767 meters on average, and the F1 score was about 0.864 on average. And especially for the distance error, first, it showed much higher values in ceiling panels, which implies that it is more challenging to interpret the targets on the ceiling than on the wall. We could also observe a slight increase in the mean values of the side panels, which are the panel number 1 and number 5 on both sides. And this indicates that it is also challenging to interpret the angle targets, even the targets that share the same surface. So These results are statistically significant with p-value less than 0.001. We conclude that these tendencies come from the pinhole projection. Human eyes see the world through the pinhole projection. So as in the bottom figure, the visible area gets smaller for the ceiling panels and the side panels. So the limited visible area resulting from projection would keep the subject from pointing precisely, and at the same time making it harder for the robot to accurately interpret the target panels. Finally, we suggest possible solutions to improve performance for spatial referencing methods in these large-scale construction environments. We could extrapolate the pointing direction vector with the two factors, distance and angle of the target, to estimate the reference points. We could also give the robot some more concrete actions, such as drawing gestures. So in conclusion, the current Deictic gesture-based spatial referencing method estimated the panels in distance about 0.767 meters, and the 86% of recognition rate. Also, the results presented worse performance in ceiling and side panels, which we concluded that the tendencies are in relation to the limited visible area. Finally, for large-scale applications, vector extrapolation with the distance and angle of the target would be possible ways to enhance the performance. We expect that these findings can guide our approaches to developing the collaborative construction robots supported with a natural human-robot interface. And these are the references, and I would like to thank you all for your attention.